For the past few years, lithium-ion batteries have been used widely in Malaysia as it eases consumers' problem. But do you know how dangerous batteries can be to the environment? This has put a question mark about the use of battery in daily life. Does anyone have the idea of how to replace lithium-ion batteries to emission-free batteries? Besides that, Malaysia has also been one of the countries that produce a huge amount of agricultural waste, which is around 1.2 million tonnes per year. This agricultural waste can be used back for many purposes. One of the purposes is to convert the agricultural waste into an activated carbon, which can be used to create a biobattery. Three types of agricultural waste can be used to develop the biobatteries, which are banana peel, sugarcane bagasse, and coconut husk. For energy storage, graphite is a widely used anode material for commercial lithium-ion batteries, which have been regarded as the best energy storage sources for portable electronics and electric vehicles. Each year, billions of lithium-ion batteries are being produced to meet the increasing market demands for various electronic devices consuming much non-renewable graphite. On the other hand, the energy density of traditional lithium-ion battery almost reaches its theoretical limit, which cannot satisfy the increasing needs for higher storage capability such as electric vehicles and green energy storage. At the same time, the poor power density of lithium-ion battery also hinders batteries' further application in the fields that need fast power delivery, for example, the accelerating and braking of electric vehicles. Therefore, it is in urgent need to develop next-generation energy storage devices to provide higher energy storage and faster power delivery using less or without using any non-renewable graphite materials. Therefore, it is in urgent need to develop sustainable alternatives for more efficient, greener and low-cost methods. Considering the whole cycle life of carbon materials from the precursor, manufacturing process to the end of life, nature renders us considerable inspirations. Naturally abundant biomass resources often possess hierarchical structures, such as hierarchically processed organization and periodic pattern, which exhibit huge potential to derive advanced carbon materials with desired properties for supercapacitors and batteries. On the other hand, biomass resources are recyclable and highly accessible across the earth, which can be not only transformed into biofuel to replace the fossil fuels, but also converted into green carbon materials by physical activation through heating at higher temperature. In fact, many carbon materials have been derived from biomass precursors, including porous carbon and nanostructured carbons with excellent conductivity and rich porosity, and exhibit potential for energy storage, catalysis, and environmental purification or remediation. Recently, inspired by natural processes such as photosynthesis and natural structures such as shells and plant tissues, many efforts have been devoted to optimizing synthesis routes to produce activated carbon materials from renewable natural resources with intriguing nanostructures, with the hope to address the urgent energy challenge. Utilization of biomass activated carbons is attractive in terms of specific capacity, ease of tailoring for desired applications and availability. Several biomass sources such as coconut husk, sugarcane bagasse and banana peel have been used to obtain BACs that have been effectively tuned for supercapacitor applications irrespective of the electrolyte medium. Lithium-ion batteries can also cause bad effects to the environment. Carbon dioxide gas, which is found in a lithium-ion battery, makes up the vast majority of greenhouse gas emissions. When the batteries are not disposed in the right way, carbon dioxide gas is released, causing greenhouse effect. This gas traps the heat from the sun and causes a gradual rise in the temperature of the Earth's atmosphere and eventually causing global warming. Lithium-ion batteries are highly flammable too. Lithium element actually is an alkali metal and its reactivity is strong as well. When the batteries are damaged or improperly packaged, lithium can be dangerous when it gets exposed to the surrounding, for example, water and oxygen. Improper disposal of batteries in landfill sites can result in the release of toxic substances into groundwater and the environment. It affects all organisms in the food chain, from tiny species like plankton through to whales. The aim of our study is to develop a biomass activated carbon using agricultural waste such as coconut husk, sugarcane bagasse and banana peel for production of electrical energy in lithium-ion batteries. Our research objectives are to prepare three types of biomass activated carbon from three different agricultural wastes, namely sugarcane bagasse, coconut husk and banana peel. We are also investigating the potential of newly developed BAC in production of electrical energy in lithium-ion battery. The materials that we have used are sugarcane bagasse, coconut husk, banana peel, sodium hydroxide pearls, manganese oxide powder and distilled water. The apparatus that we have used are glass rod, beaker and multimeter. Preparation of biomass activated carbon from agricultural waste. We have prepared the biomass activated carbon from three agricultural wastes, namely banana peel, sugarcane bagasse and coconut husk. First of all, we should wash the samples using tap water to remove the dirt. Then place it on any plate and keep it under the hot sun for at least 1 day to make sure it dries. After that, the samples are kept in the oven for around 20 to 30 minutes to remove the moisture. The dried samples are crushed and filtered into tiny particles. The powders are then burnt again at 150 degrees Celsius until they turn black to obtain the BAC powders. The powders are then kept in an airtight container. Preparation of biobattery. All three BAC powders are then used separately as an electrolyte to prepare the biobattery. An aluminium is cut into a cylindrical shape to any portable size with a cap. Then, sodium hydroxide pearls, manganese oxide powder and any BAC powder is poured into a beaker. Distilled water is then added into the beaker and the solution is stirred carefully. We must be careful when we are stirring it as it is an exothermic reaction, so the solution will be very hot. The solution is then poured into the cylindrical shaped aluminium foil and a carbon electrode is placed at the center of the aluminium foil. The cap is then used to close and has been sealed tightly. In our research, we have done 5 studies which are characterization study, electrical conductivity study, lifetime and acidity level of BAC biobattery. Characterization study is done using SEM EDX and FTIR analysis. Here is the result of SEM EDX. Based on this, we find that banana peel has most polar structure compared to coconut husk and sugarcane bagasse. In FTIR analysis, we found that banana peel has more functional group than sugarcane bagasse and coconut husk. We have also done 3 types of electrical conductivity tests, which are voltage, current and polarization and power density curve. In the voltage against mass graph, we can see that when 0.75 gram of BAC powder is used, the voltage produced is the highest, which are 1.12 volt for banana peel, 0.9 volt for sugarcane bagasse and 1.0 volt for coconut husk. Based on the current against mass graph, we can see that the current produced is the highest, which is 2 mA for banana peel, 1.5 mA for sugarcane bagasse and 0.7 mA for coconut husk. In the last test, we found that the highest power density and current density produced from the BAC biobattery corresponding to a value of 6.67 microwatt per centimeter square and 48 microampere per centimeter square respectively. Based on our lifetime of biobattery tests, BAC prepared from banana peel reached the highest current produced at 56 hours of lifetime with maximum current density produced corresponding to 91 microampere per centimeter square. Finally, the acidity level test shows that BAC biomass derived from banana peel has a pH value from 4.8 to 6.2. The other 2 BACs show a pH value close to neutral of 7 to 7.8. Product commercialization. The biobatteries are as small as the lithium-ion batteries, so there won't be any difficulties for consumers when they use it. The price will be cheap too compared to lithium-ion batteries because the substance used are agricultural waste. The biobatteries are also safe to use among children because the product is eco-friendly. As for commercialization, BAC biobatteries can be used in various fields like military and commercial applications, medical field, powering a calculator, and electrical source in electrical devices such as radio and remote control. Of BAC biobattery. There are some reasons why we have chosen these 3 agricultural ways for the development of BAC biobattery. In Malaysia, banana peel, sugarcane bagasse and coconut husk are the most abundantly available agricultural waste and are also easy to obtain and available at a low cost. These 3 agricultural wastes won't cause any harm to the environment as it is a non-flammable and non-toxic substance. It is also highly recommended because it promotes the Go Green slogan as it is eco-friendly. These agricultural wastes are also a source of renewable energy, meaning it will be used by the future generation. A significant advantage that BAC biobattery have in comparison to other batteries are it's a source of renewable energy obtained at a low cost and is environmental friendly. Conclusion. BAC biobattery are successfully developed using agricultural waste. These batteries are invented without any chemical modification. Among the 3 agricultural wastes used, we found that banana peel BAC biobattery is the most efficient and sustainable energy in the future. These biobatteries are high-performing, stable, flexible and environmental friendly. If BAC biobattery is brought to the market, this innovation will allow free safe usage among consumers. BAC biobattery has great potential as a next generation energy future. Let's go green together to save the earth. Thank you. As you can see, this is our product of biobattery. As you can see the voltmeter now, the electromotive force is 1.3 volt. And when I close the circuit, the potential difference is 1.1 volt. This is our final product of biobattery. In our research, we found out that lithium is used as the electrolyte in lithium-ion batteries. We have modified the battery using the BAC powder that we have invented. BAC is used as the electrodes and the electrolyte is the mixture of sodium hydroxide, manganese oxide and BAC powder. We have also created the most efficient biobattery by testing it with various mass and volume of BACs.